My name is Mike Onepo. I'm a program manager on the graphics team for Windows. And today I'll be telling you about some advanced techniques around graphics functionality on Windows, specifically around DirectX. In the context of this talk, I want to make sure we understand exactly what I mean by advanced graphics using DirectX in the context of Windows. And for the purposes of this talk, we're going to be breaking it down into two major themes. The first one is going to be the idea of superior 2D rendering performance. Just out of curiosity, who here has downloaded Windows 7, picked up the Windows SDK, tried out Direct2D, DirectWrite, Direct3D, all that stuff? We got one in the back there. We got two, three. Awesome. Great. So for the rest of you, this is probably going to be new information about Direct2D and DirectWrite, specifically exactly some more in-depth usage information on the platform. If you're here to learn a little bit more about Direct3D, I actually have a talk tomorrow that I'll be going into some of the technology with Direct3D 10, Direct3D 11, shaders and that sort of thing. Tomorrow at the same time, 1:30 in Hall E, I believe. The talk is CL15, DirectX 11 and Windows 7. So today we're going to be talking about superior rendering performance, understanding exactly what it means to take full advantage of the GPU. Quick review about what we've done with Direct2D, DirectWrite, and all these technologies is GDI lasted a long time in being able to provide us with a really good way of rendering pixels to the screen. But now we have these new GPUs that can, well, they're not new. They've been around for about as long as GDI has. And they've improved tremendously at being able to provide very fast asynchronous 3D rendering to the display. And we haven't been able to exploit this really in getting 2D rendering. So now we're providing this new stack that enables you to take full advantage of the GPU and all of the rasterization power that it has in a 2D context. So I'll be talking about how, while we've done things with Direct2D to improve its performance, I will be talking to you about how you can eke out the best performance using Direct2D in your application. And then the other thing I'm going to talk about today is this idea of being able to interoperate with other technologies on Windows in the graphics stack. So this goes from DirectX technologies, things like using Direct2D and Direct3D, but also I'll be talking about how to use the Direct2D pipeline in existing applications you have that might be using GDI to do rendering so that you can get the performance you need in scenarios that you can touch without having to swap out your entire backend for graphics in order to take advantage of these new technologies. So the first thing I'm going to touch upon is the idea of 2D performance. And the important basis for all of DirectX that we talked about last year in PDC 08 when we announced all these technologies is that Direct2D, graphics accelerated processing of 2D stuff, is all implemented on top of Direct3D 10.1. So this is really great. You have this nice platform that you can use to target the GPU. We've tried to make it as easy as possible to target a large gamut of hardware, and you get incredible performance in these scenarios. Last year, we showed demos where we could do aliased 2D GDI rendering, and we could do faster anti-aliased, high-quality 2D rendering using Direct2D over GDI. So we get performance improvements because we're taking advantage of the GPU. But we also get quality improvements because we have so much power behind it. So this is really great. The important thing to note when you're writing applications using Direct2D is that there are differences and subtle gotchas about how performance will work using Direct2D over GDI. And the underlying theme behind what challenges you'll run into has to do with how resources are allocated on the GPU. And so what we normally say is that when you're allocating resources, when you're putting pixels on the GPU or geometry or anything like that, the overhead for doing so is higher than it would be using GDI. The trade-off is once you do that work, you now have those pixels ready to draw at a moment's notice, and you can get those on the screen much, much faster. The trade-off is that you have to do the work up front. And this sort of drives the entire concept of getting good performance out of Direct2D. And the mnemonic that we use to try and get people to understand this concept and how to work with it and the right strategy, we kind of use this sort of eco-friendly model of reduce, reuse, and recycle of all of the resources that you have in Direct2D to make sure that you avoid any unnecessary costs around this large overhead for allocating resources. So the first one I'm going to talk about in this is just the idea of reducing your complexity, controlling your scene complexity to make sure that you're getting the best performance you can. Then reuse is this idea of caching intermediary data as you're rendering in order to reduce the amount of work that the GPU needs to do. And then finally, I'm going to talk about recycling, so repurposing already created resources, bitmaps, render targets that you have, so that you are not incurring the cost of having to destroy and create resources over and over and over again. And a lot of the slides I'm going to be talking about today assume some basic knowledge of Direct2D. I'll be walking through some code, so if you're not familiar with it, you should be able to see it in action. And if you have experience with GDI, this should be pretty familiar. It's about the same scenarios that you might be wanting to try. OK, so let's talk about the first thing, which is this idea of controlling scene complexity. And this is less about specific tactics and more of the way to think about how to make sure you understand where your performance bottlenecks are and making sure that you understand when scene complexity is interesting. And to understand this problem, I'm going to talk about two issues. First off is understanding the concepts behind fill rate bound applications and scene complexity bound applications. And then we're going to talk about how to improve your performance in each of these cases. So improving fill rate bound cases and improving scene complexity bound cases. So what do these terms mean? When you're looking at the rendering pipeline for Direct2D or Direct3D or any of the DirectX technologies that we're talking about today, you're involving the GPU. This means that you have two possible places where a lot of work can happen. One is obviously on the CPU. So that's what we have. That's when we have scene complexity. And the idea behind this is that when you're doing a lot of work on the CPU, say you're doing a lot of processing before it is even sent to the GPU, you're going to have this concept of scene complexity. There's just a lot that the CPU needs to be running on and churning on before it can submit anything to the GPU. And you're going to see this as a problem when your GPU is essentially sitting idle and waiting on the CPU to do something. The other case is that the CPU is relatively idle because the tasks you've sent down from the CPU are done. They're finished. They did the processing. But there's a lot of work that needs to be done on the GPU. We call this fill rate because the most common problem that you run into is that you're drawing very, very large geometries or very complex geometries where it just takes a lot of time per pixel that it needs to fill. So the rate of fill that you have is what's slowing you down. So how do I tell the difference between these two without having to hook up wires into my GPU to see exactly what it's doing? What's the quickest way for me to do this? Well, the observation we make is that when you have this idea of fill rate as potentially the problem, you have a lot of pixels to fill. So how can you most quickly reduce the number of pixels that you have? Reduce the total area that you're rendering to. Reduce your render target. If you reduce the size of your render target to something much smaller, fewer pixels, and you see a significant performance improvement, you pretty much are guaranteed that you're fill rate bound. If that doesn't provide any significant performance improvements, chances are you have too much complexity, too much stuff that you're running on the CPU, and that's what's really slowing down your machine. And that's not the case. That case is actually the one we really want to avoid. The moment you have it so that the CPU is doing a lot of the work, you're losing a lot of the benefit of having the GPU at your side. You almost always want to be in this case where you end up being fill rate bound, because now the GPU is busy doing what it needs to do, and the CPU is free to do other stuff, like, say, run your application instead of running all the graphics for you. OK, so we have this concept of fill rate bound versus scene complexity bound understood. What do we do? Well, in the fill rate bound case, the most logical thing to do is to make sure that you understand the exact number of pixels you need to be rendering and only render those. If you're going and allocating a very, very large texture memory, something like 2048 by 2048 to render to the screen, and you really are rendering, say, to a screen that's already 1024 by 768, you're doing too many pixels. This seems pretty simple, and chances are you've this is going to be the first thing that you look at, is making sure that you're allocating the right render target. So what else can we do? Well, there's this idea of overdraw. Who here is familiar with the idea of overdraw in rendering? OK, so pretty familiar with this idea. I'm still going to quickly go over it because this is something that we encounter, and there's some little gotchas about it. And we break overdraw into two situations. One is occlusion, and the other one is clipping. And to think about this scenario, I have this this example application I'm writing, and it's drawing some kind of 2D texture in a background. In this case, it's just really simple. It's just some circles so that I can break it up easily. Occlusion is the idea that when you render something over this, there's a bunch of stuff that you're drawing that is ending up not on the screen. Even though you might be just doing a quick array draw of all those circles on the screen, and then you put something over it, you've lost some performance. This is a pretty trivial case. I'm only talking about 8 circles that I could be drawing, but that's lost time. Those pixels had to be drawn twice, once for the circle and then once for this big rounded rectangle. So this is a trivial case, but you can imagine a situation where this could scale very, very large. I have complex patterns, complex backgrounds that I'm drawing, and then suddenly I put something in front of it, and I've wasted all that time on those pixels. So that's the idea behind occlusion. Clipping is another pretty simple concept to understand, which is that I do the pattern, but I do the pattern in something that is a little bit larger than the actual display is available. So this box represents the actual pixels that are getting put out to the render target. The things off the screen are clipped off. Now we do some performance improvements to try and reduce clipped geometry, but at the end of the day, you've still done all the work to actually draw that circle on the screen. This is all wasted time. So a thing that's going to improve your fill rate is if you can figure out these cases intelligently and make the right execution. And it's trade-off. You're doing something on the CPU to reduce the work of the GPU. OK, so now we talked about fill rate. What happens in the case where you're talking about scene complexity? And scene complexity really ends up being a problem. We don't see it as being something where people are doing unnecessary work. They're choosing to do very high-quality rendering. And very high-quality rendering, things like anti-aliasing or complex brushes and effects or sophisticated geometry, these are scene complexity. They increase the scene complexity when you add these things to your scene. So these are good to have. They mean that your application is very rich. It looks great. But you're going to be always doing this trade-off between that quality that you have and the performance that you have. So for the rest of the talk, when I'm talking about 2D performance, I will be talking about these scenarios where you can reduce the quality in order to get a performance improvement. And then you can make the decision. You guys can go and you can write your applications and make a decision about whether or not you want to be trading off that quality, or you think that the quality is something that you can afford to lose. And I'll be giving some examples of where it wouldn't really make a difference from the actual pixels that end up on the screen, versus making sure that you get the performance that you need. So that jumps us into the next section of our little eco-friendly diagram, which is reuse. So this idea of caching intermediary data. And I'm going to be talking about 2 techniques. The first one is this idea of grayscale caching, or using A8 resources. I'll talk about what that means in a second. And the idea of meshes, and being able to do mesh caching. So the first thing, obviously, is this idea of an A8 resource. What is an A8 resource? It's something that is very useful for rendering text, opacity maps, or otherwise grayscale content. And what A8 stands for is an alpha-only channel, so a value from 0 to 255, because it's storing 8 bits per pixel. So you can imagine that this is storing one number from 0 to 255 per pixel in your buffer. That's stored on the graphics card. Why is this interesting? This is interesting because in a lot of cases, you're representing your data as some shape, say some text, some geometry that you're trying to render, and it's just a shape. It's something that's there, it's not, black or white, or sometimes with some transparency. So sometimes it might be interesting to cache all of that complexity into a single texture, and this is by far the most efficient way to do it, is you can just store these pixels as a value from 0 to 255 and render it to the screen. Well, how do I use these? We make this really easy. We have this idea of a compatible render target in Direct2D. You create it off of your existing render target, and it is something that you can use to do off-screen caching of information, like these A8 resources. You pass in this pixel format that we have here, A8 and UNorm, and now you have something that just has this one channel. You can cache any texture data that you want into that, and then you can render it using this special function we have called fill opacity mask. What this does, you can provide a brush, which is essentially a fill effect, something like a gradient or a pattern, or even just a solid color. And it will fill in any pixels that are essentially the highest value with the full, that 255, with the full pattern, and 0 with none of it at all, with some completely transparent, onto the render target. So I'm going to give a demo of exactly how you could use this for, say, caching text. So let me quickly pull up the demo here. So what I have rendering here is some text using DirectWrite to render it using our fancy Gabriola font. And this is actually, this is true about every sample that I'm going to be showing today. They're all available today on Code Gallery. So if you have your laptop out, you can actually go on Code Gallery right now. You can look at the text animation sample, and you can play along at home. So in this sample, what we have is we have text being rendered using DirectWrite in a very simple manner. It's just being drawn directly to the screen. And you can see we can actually animate this. This is hardware accelerated, so we can get some really great animation. I'm going to turn off the translation, so it's just in the center of the screen. And I'm going to turn on a zoom effect. And you can immediately see a couple problems. For one, our frame rate is OK. It's around, say, it jumps around, but it can go anywhere from 30 frames a second to about 100 when we're lucky, when things are really small. In addition, we're finding this issue. I don't know if it's something that's very clear here on the screen, but you can see there's a little bit of jittering. Does everybody see the jittering that's going on? That's the DirectWrite layout engine and ClearType. It's doing snapping of the text as it scales the font size. And this is because mostly this system, the hinting system in fonts, is not meant for this kind of zooming situation. It's meant for a fixed size. So we have a bit of an artifact from using, this is the highest quality path. This is a nice, anti-aliased, beautiful path. But there are some issues the moment I want to animate. And animation is something that we're really trying to enable with a lot of these platforms. How can I solve a couple of these problems? How can I get my performance better and get a smoother animation? Well, what I can do is I can cache the text to an A8 resource. And I'm going to go ahead and do that right now. Now, you immediately see the frame rate jumps way off the roof. It's not obviously drawing at that speed. It's just sort of re-rendering it that quickly. We're in the thousands, because pretty much all it's doing is drawing a single texture and zooming it in and out. The next thing you'll see, OK, so it also seems a bit smoother. And that's not just from the increased frame rate. That's also because you're losing that jitter. But there's one trade-off. If you guys notice, as it scales up, let's actually see it scale up for a second. You get one way to look at it is pixelating. What's really going on is it's doing a linear filter. Hardware is really fast at just sort of figuring out values that are linear between the different pixels. So we get what's called a bilinear aliasing artifact, or upscale artifact. And so that's the trade-off that you have. We've got this great performance. We've got a smooth animation system. But we've had to trade off some of the quality that we might have. Well, to show you guys exactly how this code works, I'm actually going to go ahead and walk through it. I have the demo up here. And so I'm going to go ahead and turn on some breakpoints. I'm going to go ahead and run this so that you can see what exactly it's doing. So again, we're going to go ahead and turn on that caching. And we'll immediately hit a breakpoint. And the first breakpoint that I've turned on is setting up this cacheable resource that you can use. And like I said before in the slide, and this is just to prove that I'm not lying to you, that this code actually works when you go and do these cases, we create this alpha-only format using that A8 unorm DXGI format that I referred to before. And then the next step is to simply use this create compatible render target function. And that gives us this result of p opacity RT, which is the render target we can use to cache this once and render it multiple times. This code is run exactly once in the application. The next step of what it will do is if we've succeeded in creating those resources, it'll draw the text to the screen. Very simple. This is exactly the same code it's using to draw that text to the screen directly, only now it's doing it once and caching it to this off-screen render target. So we begin draw. We clear this opacity render target with some transparent value. We draw the text in, and we're done. OK, so now we want to actually draw this to the screen. You'll see that, and this is, I stopped the code a little bit before we actually call the draw to point out one important thing to note about using this technique, which is when you're using a brush that has specific metrics, say a pattern brush, you do have to normalize against that and make sure your transforms match, because things are going to be slightly different in the way that a texture map is rendering over just some geometry. So make sure that your brushes match up. Another thing to note, and that's actually what this code is, Direct2D, if you guys may or may not know, has a concept of DPI awareness. As you scale up and down your DPI, if the screen is very, very high DPI resolution, so a lot of pixels in an inch, other than the displays I have here, which are mostly at the standard 96, it's aware of that, and it will provide you the proper metrics. But when using pixels directly in textures, you need to be aware of this. So the code that we have here sort of normalizes against the DPI. So that's what the math here is that I show. And then finally, what we're going to do is using that p opacity RT variable that I showed before, we can get a bitmap out of that. We store that in p bitmap. And then I can simply use that to fill opacity mask, that exact API I talked about before. And we just pass that bitmap, and now it's rendered to the screen in the right place, and we're good to go. So then when you've done that, you get this really smooth rendering at a very, very high frame rate. OK, back to the presentation. I left it running over here. That's not so good. OK. A quick note about using DirectWrite and getting performance out of DirectWrite. And this is a scenario where you are trying to enumerate all of the fonts in the system, or you're just trying to enumerate a single font, and you're trying to get the best performance out of that. And you can immediately see this scenario when you're trying to create that little list view box that gives you all of the different fonts in the system. Making that list, we have a way of getting the performance better on that. The actual practical way you get a font to apply it to text, like what I was doing before when I said draw text layout, I had to apply a specific font, that Gabriella font. I use a font face, which provides all the information about how the font should be used. It's how you actually assign the font. You understand the text features that are available to it, how you can measure the text to make sure it's fitting in the right area that you want on the screen. DirectWrite's really sophisticated in being able to provide this. But that full interface requires a lot of memory and a lot of storage in order to get it to work, and it's a little slower. When you're just trying to enumerate all the fonts in the system, we have this idea of a DWrite font. It's a little bit more lightweight, and it's just about getting some basic information about the font so that you can just enumerate every single font in the system. So yeah, this is faster to load. It takes up less memory. You can load up a bunch of them as you're trying to get your font information, and this will give you a better performance in those scenarios where you're just trying to enumerate the fonts in the system. OK, so then the other technique I was going to talk about today is this idea of meshes. So this is a bit of confusing terminology. There's an idea of a geometry in Direct2D, and a geometry is a shape. It is a definition for a shape that you can populate. And it includes things like Bezier curves, straight lines, a rectangle, an oval, anything you want. A mesh is a conversion of a geometry into actual triangles. Because remember, a graphics card is very, very fast at drawing triangles. That's what it's designed to do. It can take billions and billions of triangles and render them very, very quickly. That's what the card is designed for, in a parallel manner, to be able to get those onto the screen. We're based on the Direct3D pipeline, which, if you remember, its sort of ancestry is in gaming, where you would have these very large 3D models that were made out of triangles. So a mesh is a 2D representation of some kind of geometry realized into triangles. And because it's in triangles, it has to be aliased. The idea is that we can't get any smooth edges. It has to be something where it's exactly the pixels on the screen. But it's much faster to render in Direct2D. Direct2D is much better at being able to render this type of data. So let's walk through the steps for how you could potentially cache this. And this looks somewhat similar to the A8 resource example I gave before, in the sense that I'm taking that data once, putting it in some kind of buffer, and then being able to use it multiple times. And this is very simple. A mesh has this open function, which returns a tessellation sync, which is essentially an interface that lets me start feeding triangles to it. And so I can then, any geometry has this idea of a tessellate function, which takes that tessellation sync and starts filling in the data. Very simple. And then once I have this mesh that I've created, I can use fill mesh to draw it. And this acts exactly like that draw opacity mask. I can just fill the mesh with any kind of brush that I want to have it use. And again, I have an example to show this. But one thing I want to really point out that's kind of cool about this is that D2D1 tessellation sync, that idea of being able to feed geometry into a mesh that I can draw later, I can actually write one of these myself. I can actually implement this manually and see the triangles that are coming out of the D2D1 geometry function directly. This is actually the best way to pick those triangles up if you wanted to use them in Direct3D. But the cool thing about this is now you can see exactly how the D2D pipeline is doing its tessellation, and potentially use this in other scenarios where you might not want to use Direct2D for your direct rendering. And that's sort of alluding to something I'll show at the end. So first thing I want to show, though, is I want to show this idea of geometry realization. And that's sort of the terminology we use to talk about this idea of converting a geometry into actual mesh, the final thing that gets rendered to the screen. We call that realization. So let me go ahead and open up that sample for you. And what you're seeing here is you're seeing a bunch of hourglass shapes being rendered using a brush that sort of does this gradient effect. And they're being rendered using just a straight up geometry. So this is not using any kind of mesh. And you can see that the performance is pretty good. We're getting about 60 frames a second. I can actually up the ante a little bit here and get a whole bunch more of these. And you can see the frame rate drops pretty quickly. Now we're on the 6 and 7 frames a second. Actually, now it looks like it's more at around 5. However, if I go ahead and turn those into meshes, you can immediately see the difference in performance that we have here. So I'm drawing a lot of complexity here. These are a lot of triangles. But because graphics hardware is very good at drawing these triangles, I've got this great case. An important thing to note is that this is set up to be aliased. Again, this is a situation where the only way that you can really use these triangles right now is in the case where you're OK with not getting those nice smooth edges. If you want to see sort of the difference of what you would have here, if I go back to the unrealized case and drop this down a little bit so you can see it, this is aliased, and then if I can turn on anti-aliasing, you can see the difference in quality. OK, so how does this demo work? I'm going to go ahead and turn on some breakpoints. We're going to run this so that we can see exactly what happens. So the first thing that's going to happen is we're going to be filling the mesh. And this is exactly the code that I showed you on the slide. Again, I'm just trying to not lie to you. So we can create a mesh. We go ahead and use this. We create a tessellation sink by using the open function. And we can use the tessellate function to populate it. Once we're done, we go ahead and set stroke mesh to be the actual mesh definition. We just store that data. And now we're ready to use that to draw. So if I can continue through to the rest of the code, and then I go ahead and I realize the geometry here, I hit a breakpoint. And you can see that this function is very, very simple. I provide some brush that I want to render. In this case, it's that nice, cool gradient. And I just use that mesh. So a very simple way of sort of swapping in the code. That's actually one of the major things we tried to do with some of these performance aspects of Direct2D, was this idea that we could make the code be something that you've written your application in the way that is simplest to do, where you're just taking your data and you're drawing it to the screen, and now you need to see, you have these specific cases that are costing you a lot of time to render them on the screen. Well, we provide some way for you to do these performance improvements, A8 caching, geometry realization, and just swap them in by doing a little bit of extra code. And then the actual call in your draw is a very simple change. Instead of drawing a geometry, you draw a mesh. Instead of using draw text layout, you use fill opacity mask. We make it as simple as possible. OK, again, back to the presentation. OK, so I've talked about the idea of being able to reuse resources, reuse stuff as you're rendering, sort of caching things in the interim. The last thing I want to talk about today is the idea of repurposing already created resources. And when I say resource, in this case, I mean something like a render target, something that I'm rendering to, or a bitmap, actual pixels that I'm rendering to the screen. And as I've rendered things to the screen and I no longer need those bitmaps, don't go and throw away that resource. Keep it around so you don't have to incur the cost of having to recreate it. So the first thing that I'm going to talk about is the concept of surface size, so bitmap size, render target size, and how that might impact performance. And there's some really interesting things about how that works on a graphics card. And then finally, I'm going to talk about tiling or atlasing on resources to improve performance by conglomerating the pixels that you might be using onto larger resources. So the important thing to take away from this presentation, if I say one thing, is going to be this idea that we generally recommend that you allocate bigger surfaces. And this seems really counterintuitive. Wouldn't it make sense that you want, I said earlier, I should be rendering to the lowest number of pixels possible. But why on earth would I be wanting to allocate larger surfaces? And just to be specific about what I mean, I don't mean that you should just be going and allocating thousands and thousands of pixels. What I mean is that we favor multi-purpose, larger textures over single-purpose, smaller textures. What's an example of this? Let's say I'm rendering a whole bunch of icons on the screen, scattered everywhere. Each one is roughly the same size, except for a few that are a little bit larger. As I'm iterating through, I might be pulling these off of the web or something. I'm trying to get all these icons. So I'm very quickly populating a bunch of bitmaps and drawing them to the screen. OK, so we have our scenario. There are a couple ways I could do this. One is for every single bitmap that I need, figure out the size, allocate a bitmap, render that to the screen, throw it away, do the next one. That is exact size, smaller, not reused surfaces. You've incurred the cost of creating each one of those resources and throwing it away every single time. Instead, why don't you figure out close to what the largest bitmap that you have is? Allocate that once. Just allocate one. Fill in the pixels you need, render it to the screen, replace, fill it again. Now I don't have to go and create destroy resources, but I had to go and I had to create one larger bitmap. So we recommend that you still really only allocate what you need, but there are scenarios where you can get performance improvements by allocating more pixels. And the reason why this is interesting is because on a graphics card, the minimum size tends to be around 64 kilobytes in texture size. You can't really go any smaller than that. So for something that might be 24 bits per pixel, so a red, a green, and a blue channel at 8 bits, this ends up being about 150 pixels by 150 pixels. This is not really a texture that you would be using commonly, so we normally recommend, and sort of by doing the math out, that you make it so that the smallest texture you ever allocate is around 256 by 256 pixels. This is pretty big. This is actually something that could easily render some kind of icon. And the reason why is because the graphics card incurs this overhead when I need to go and allocate these bits. Once they're there, they're incredibly fast to use. So I want to be creating these larger multi-purpose resources that I can use blazingly fast instead of having to incur this overhead to go and create and destroy everything. So what about the other way? I'm telling you to create bigger textures. What happens when I need to go big? Well, unfortunately, the maximum size varies per card. Most cards that Direct2D can target are around 2048 by 2048 pixels that it can allocate. But some of the really cool modern cards, the cards I'll be showing off at the DirectX 11 demo tomorrow, they can go up to pretty big texture sizes, 4096 by 4096. These are pretty big. It's reasonable to assume that that's sort of 2000 on a side. It varies, which is not ideal, because now you have to sort of dynamically figure out what it is. But luckily, we provide a convenience function that lets you figure this out. Using a render target, the render target is specific to a graphics card, so we can just ask it, what's the maximum texture size? And I can use that. And then the size is in pixels. An important thing to note about this API, in the documentation, we're currently trying to fix this. Documentation says that the size is in bytes. It's not. It's in pixels. It's important to note. So 1 pixel width size. OK, so the last thing I want to talk about when it comes to reusing resources is this idea of atlasing. And another word for this would be tiling. And what we mean by this is, let's go back to that case where I'm allocating a bunch of bitmaps to render some icons to the screen. In fact, I'm going to be giving a demo of exactly that case in a second. The naive way to do it is, let's say I had 5 256 pixel wide bitmaps that I want to be rendering. The naive way to do this, allocate 5 bitmaps. Great. So each one of these is a bitmap allocation. Well, that's good, but now I've done that 5 times. How can I make it less? Well, I could make one allocation, say 256 pixels tall by my maximum texture width wide, and start populating that with them, and tile it along the texture. Now, there's one issue with this, which is that as I start filling that up, you can see that I have 5 of them, so I'm going to have something that might run off the edge. Well, that's an interesting scenario. So really, what we recommend that you do is you do a 2-dimensional tiling. So you allocate a large resource, and you start filling the data in using a grid instead of just a line. So this is the idea of atlasing. And we've tried, like all the other techniques I've shown today, we've tried really hard to make this very easy for you so that you can swap it in as necessary. And the way we've done this is we've made the draw bitmap function have the concept of being able to draw a subset of a bitmap that you have. So we recommend on your end, if you're choosing to do this scenario where you're allocating these larger resources, you create some kind of atlas bitmap class or struct. And this is a very small struct. It just contains the idea of reference to the bitmap. So in C++, this would be a pointer. And in managed code, it would just be a reference. And an offset in size. You can actually hold all that information in a rect. And all that is if you go back to that previous example I gave with the big atlas, it's just the section of the bitmap I want to draw. OK, that's cool. And this pretty much provides you everything you need to use the draw bitmap function that you were using before in the naive case, just now with this concept of an atlas. And by the way, we have a bunch of functions that allow you to do hardware updates of atlas of bitmaps very, very quickly. So an example of this is this copy from bitmap function. You can copy bits around using the GPU and never involving the CPU. It doesn't have to read the pixels back onto the CPU. So you can get really good performance as you shuffle bits around on the system. OK, so I have a demo to sort of prove that I'm not lying to you and that this is something that you can get pretty good performance out of. Now, we generally recommend that you don't go and you implement the scenario of an entire list view system, like the one that I have rendered here, using Direct2D. We've got a system for you for that. It's called Windows. So the thing that we tried to show off here when we're doing this example is something that draws a little bit more animation to it. So it's got a little bit of inertia on the flip, and then when you actually change the directory that you're in, it does a little cool animation, just to show that it's doing this in real time using the GPU. And the thing to note about this application is every single icon you see on the left we're using a bitmap atlas. So let's actually take a look at the code to understand exactly how that works. The first thing I want to show you that I have open here is you can see I have this item info class. This is a little bit more compact version of that bitmap atlas idea that I talked about before. We have one atlas that we're using, so we don't go and make sure that we have a reference per bitmap, per item info. By the way, each one of these represents each of the items in the list of that list view. Very simple representation. That is just this placement rectangle that you see here. This is the offset rectangle inside the bitmap atlas. And then the next thing is the file name. So you can see that we're pretty much just providing all the data we need to render that to the screen. OK, so we have this struct. How do we use it? So I'm going to immediately hit a breakpoint. And this breakpoint stops while we're in this load directory function that we have on the sample. Again, I encourage you guys to check out the samples on Code Gallery after this presentation. And what this has is this is essentially what's reading everything off the file list, all the directories on disk, and it's populating the entire directory so it can render it. So what it needs to do, it figures out the file name, it figures out if it's a directory or not, and then it populates the bitmap on that bitmap atlas, and it figures out what the sub-rectangle is that it needs to draw when it needs to draw that icon. So the first thing so let's assume that we've gone ahead and populate the pixels, and now we have this running counter. If you were to visualize this atlas, you could imagine that there's a cursor sort of working through it that indicates the upper left-hand corner of the next bitmap icon that we could put in the texture. That's what this current x and y is that's being referred to here. And this is essentially, I'm just going to quickly walk you through the code for how we populate all of the icons into this texture and do the right thing to make sure it populates. So we go ahead and we use the current one we use this current x and y to populate the placement of the left and top-hand corner of the current icon. And then we want to advance these pointers onto the next one. How do we do that? Well, sort of like moving in a typewriter fashion, we just move to the left a width of a icon so that the x value is now incremented. But what happens if we exceed the size? So if we go back to this code here, if we exceed the size of the width of the atlas, well, we would then sort of hit the carriage return key on the typewriter, move back all the way to 0 in the current x, and move down one row in the y direction. And then the last bit of code, because this is a sample, if there's a very, very, very large number of icons, we simply won't draw them past, I think it's a couple hundred, just for an ease of understanding the sample. But this is a place where you would have the opportunity to maybe go and use another texture that you've allocated to further fill other atlases. OK, so I've gone ahead and I've done this population of everything, and I want to render it to the screen. So this is the actual call that does it. And this is exactly how the draw bitmap call would look when you're drawing that icon to the screen. Except this last parameter here, if I scroll down, you'll see I'm using that placement rack to just indicate some offset in the bitmap. So this is easy. I just take this large bitmap instead of a single bitmap that populates my entire icon. I have them all in an array, and I provide a subset. I can render it. OK. So that's really cool. And if we actually turn off all these breakpoints, we can see this cool application running again. You can see this initial sort of bounce effect that we have. And all this can run in real time and is very fast. It does one texture allocation in order to render all these icons. And that's really cool. OK. The last section of this talk I want to cover is this idea of DirectX interoperability. So being able to use Direct2D, DirectWrite, Direct3D, and GDI together. I'm going to talk about a couple things. Understanding Direct2D fallback and how the system works when you might not have as good of hardware as you'd like, or you just don't have any hardware at all in the system. I mean, we're talking about exploiting the GPU, but we want to make this a system that works on every possible configuration you have. What does Direct2D have to offer in those cases? I'll talk about using Direct2D in GDI. And again, this is the scenario we're talking about where you have an existing application, but you want to replace some high-performance scenario or some high-quality scenario with Direct2D. Then finally, I'm going to talk about how you can use Direct2D and Direct3D together for scenarios where you're drawing 3D content into 2D content and vice versa. OK, so understanding Direct2D fallback. Direct2D natively runs on Direct3D 10 class hardware. We've talked about this before. What if you don't have 10 class hardware? That's a premium logo requirement for Vista. But what if I don't have that hardware available? Well, I might have 9 hardware, Direct3D 9 hardware. So we have this new component in Windows 7 called Direct3D 10 Level 9. And essentially what this is a component that enables the Direct3D 10 runtime and Direct2D to run atop of 9 hardware. And this happens automatically. Direct2D will go ahead and just use this. If you have Direct3D 9 class hardware, you won't even notice. It'll just be able to draw, and it'll get great performance and utilize the GPU. For cases where you don't have any hardware at all, or you have a very low-end machine, or the third case, which is that you really care about making sure that it's an absolute pixel-perfect representation, and you're willing to trade off some performance to do so, because keep in mind, a graphics card is we're very strict in how the standards work for making sure that your floating point precision is right for some of these sampling aspects, but it can never be perfect. There are different implementations, so you might want a pixel-perfect representation. We have a software fallback. If your render target creation fails because you don't have hardware, you can pass in this software flag. There's a default option in creating a render target that will automatically fall back to software. So if I go ahead and use that default render target setup, it'll hit Direct3D 10.1 hardware if it's available. It'll go to Direct3D 9 hardware if it's available. Otherwise, it'll go through a software path. And you'll find actually that software path is even pretty darn fast for rendering your 2D scene. So this is a really great, very transparent way to just exploit what the system has available. OK, GDI and Direct2D interop. Really, the way that we wanted to make this happen was, and this is the case I'm really going to focus on, I want to have some piece of my application that's written GDI rendered using Direct2D. So I throw away the small bit of code that I was originally using GDI. And then I can go ahead and Direct2D create a DC render target. And this is a specially designed render target where I can bind a specific HDC, handle to device context, that I would be rendering using GDI, and just render using Direct2D instead. So this is a really simple way of going ahead and doing this for you. A couple things to note about this is make sure you've called ndraw in Direct2D before moving on to any GDI calls. This is important because ndraw is really the time that Direct2D tells the GPU, hey, I've got all these drawing calls. I need to actually execute them. It will batch them up and call them on ndraw. So if you don't do that, you're probably not going to get anything rendered to the screen at all from your Direct2D. And then this is a concept that is pretty important across using any 2 APIs together. You want to batch the calls in any single API as much as possible, because the transfer from one to another can sometimes be very costly. That bind DC call that I referenced in the other slide, once, twice, 3 times a frame, should be fine. The moment you start doing that between every single draw call, you render a line, and then you end draw, and then you switch over by binding DC and draw something in GDI and switch back and forth, you're going to see significant performance loss. So we really recommend that you batch calls together as much as possible. And then if you notice in the bind DC API, again, there's this idea of a rect, and that's the actual pixels that you want to have updated. Get that to be as small as possible to just the pixels that you're actually updating on your GDI DC. Because that means that there's less that it needs to transfer, and that will give you a performance boost. OK, let's talk about rendering Direct2D content using into something like a Direct3D situation. And the example that we give here at the top of the slide, I have ID2D texture, ID3D10 texture 2D. That's the off-screen representation for pixels in Direct3D. This is something I can use to apply a texture to a 3D object in Direct3D, or maybe just provide some triangles that are in the 3D scene that move around. I can render into those pixels using this concept of a DXGI surface render target. I pass in my texture 2D into this function, and I can now render using Direct2D into this surface and use it in Direct3D. This might be interesting when you have a 3D game or some 3D scenario where you have, say, a character that's rendered in 3D and you want to render, say, a chat bubble over its head. You could render the chat bubble using Direct2D, cache all that data into a surface, and use it in your 3D scene as necessary. Going the other way, we've also made as simple as possible. When would I want to do 3D into 2D? I think we can imagine a couple scenarios. The one I always like to think of is big, long text layout, and inset is maybe a 3D object that's moving. This is a possible scenario, and actually a really cool one. And the way you do it is using a shared bitmap. And a shared bitmap is essentially taking one of these texture 2Ds that I have in Direct3D and creating a bitmap out of it. So by creating this shared bitmap using this API, I can provide the pixels of some end result 3D texture into Direct2D. A couple things to note about this. You must pass in a DXGI surface, just like anything before. And then the bitmap properties that you pass here have to match the format of the surface that you're using in Direct3D. A nice convenience about this is because the idea of alpha differs between Direct 3D and Direct 2D. We don't check for the alpha value. It's pretty much just the red, green, and blue channels and what the bits per pixel are on that. Some things to note about doing this kind of interoperability. The device that you're using in Direct 3D must support a special set of pixel formats that should be familiar to you if you've been using GDI, called BGRA formats, just a different ordering. Instead of it's starting with the red channel, it starts with the blue channel. And it must be using the Direct 3D 10.1 runtime. Now, that doesn't mean you need Direct 3D 10.1 hardware. It just means that you need to be using the Direct 3D 10.1 runtime, which is just a newer runtime that we provided in Windows Vista SP1. It's as simple as just linking to d3d10_1.lib instead of d3d10.lib. It's the only difference. And once you have that availability, you can then go ahead and use this interop properly. An important other thing to note is that this BGRA support requires a new driver. For the most part, graphics drivers that are available in Windows 7 already have this support, so you're good to go. You can check using Direct 3D if it's possible. In fact, the quickest way to check is that you have to create your device using this special flag, create device BGRA support. And if that fails, you immediately know your driver doesn't support it. And not to worry if that happens, you can use Direct 3D 10 Level 9, which guarantees BGRA formats at all times. So you're never left out in the cold. If you want to do this kind of interop, you could choose to use Direct 3D 10 Level 9 instead. Another piece of recommendation, and this should sound really familiar, is you really want to be caching existing content in Direct 3D. If you're not updating that content in any significant way, don't re-render it. You're wasting time. And then this should sound really familiar. You should minimize the transitions between Direct 3D and Direct 2D as much as possible, because switching between them can get expensive. The last thing I want to show you guys today is I alluded to this pretty obviously when I was talking about using the tessellation to create a mesh. And I've been focusing a lot on the idea of interoperability by transferring pixels. Transferring 3D rendered stuff into 2D, and taking 2D stuff into 3D, using Direct 2D and GPU accelerated stuff in GDI. Are there other ways I could potentially do interop? And the example that I want to show, just bear with me a second here to open it up for you, is a situation where instead of doing it using pixels, we're doing it using geometry itself. Now remember how I said that I could implement the concept of a tessellation sink using myself. I could actually go and I could implement a tessellation sink and do whatever I wanted with the geometry that is created from Direct 2D. Well, this is exactly what I'm doing here. Instead of drawing the triangles using Direct 2D and doing acceleration using a mesh, I take the triangles, I load them into Direct 3D. So to be clear, I take my text, I convert it into a geometry. I take that geometry, I use that tessellate function, I feed each triangle into Direct 3D, and then I can render those triangles using lighting and cameras and transformation matrices. And in addition, what we've done is we've also extruded the text outward so you get some actual 3D shape to it. This is another demo that we have available on Code Gallery, so you can try it out. And it's a really cool way of sort of showing how you might be used to thinking of things as being in pixels, but we can actually now take advantage of geometry in order to make this happen. So this is a pretty cool sample to do. OK. A couple last pieces of cleanup, making sure you get the best development environment in doing Direct 2D. We have recently added this. This is really cool. This concept of a debug layer into Direct 2D. And a debug layer is something that intercepts calls between the application and Direct 2D and starts collecting data for you. And as it sees you do things that might be wrong, let's say a creation fails, it'll tell you. It'll say, hey, any critical usage information you needed to know to understand why this thing has failed, we'll tell you some additional information out of the debug output. It also, this is important to note, by doing so, it pretty much leaves the operation of Direct 2D unchanged so that you can make sure that your application continues to run exactly the way that you want it to. You get a little bit of a performance loss, though, because it has to inject itself. But now you have all this incredible debug information that you can use to understand fully why things might be going wrong in your application. Let's look at an example of where this, actually, really quickly, let's just walk through how to turn it on. It's really easy. You pass a flag into create factory. Easy as that. You can take all the code from all the slides I have here and just go ahead and drop it into your applications. It all works. So here's an example of a situation where you might be running into a problem. I'm not going to go into the detail of exactly what a layer is scenario-based, what scenario we wanted to have the layer for, but essentially it's a way of you to be able to render a bunch of stuff into an off-screen surface and compose it using transparency onto the main render target in a very quick and easy to understand manner. This is great when you have alpha blending or non-rectangular content that you're needing to compose into a larger scene. What if you aren't doing that? What if you don't need alpha blending or you have rectangular content? Well, we have this idea of an axis-aligned clip that uses a special hardware function called scissorRex to optimize this case much faster. Well, and by the way, these are the APIs that you can use to go ahead and use it. Well, let's say you're using layers, but the scenario you're using it really could just use an axis-aligned clip instead. Well, the debug layer will tell you. It'll say, hey, you're using a layer when a clip is sufficient. You could be getting a lot of performance improvement out of this. And it'll just go ahead and tell you that. So it also provides this one piece of performance information, which is really cool. The last thing I wanted to mention today, I've been talking about this as if it's something that's really only available on Windows 7. We talked about this before. Very proud to say that we can provide all these technologies currently on Windows Vista as well. Through a Windows update called the Platform Update for Windows Vista. So this allows for the entire DirectX platform, Direct3D, Direct2D, DirectWrite, DXGI, and a bunch of other technologies that I haven't listed here today. But I've provided the KB article for you if you'd like to check it out, so you can learn all of the great things that we've provided also on Vista to help you and get your application out onto the largest number of computers that you can today. You can take everything I've talked about today, hit people with Vista machines and with Windows 7 machines. Pretty awesome. So here's a quick list of the resources that are available to you. We have a DirectX MSDN site where you can find all these code samples in a nice browsable fashion. The Windows 7 SDK. If you're interested more in the Direct3D side of the world and how 3D works, we recommend you download the DirectX SDK. The 2009, August 2009 is the latest version. All the code samples are on Code Gallery. This is every single one that I've provided, so you can try them out yourself. And finally, the debug layer is available on Code Gallery. You have to download it and you have to install it. It's not part of the Windows SDK, so make sure you check out this link and get it running on your system. So that's my talk. Again, we want to say that your feedback is very important to us, so please fill out your slides. And everything that I just talked about, and pretty much all the presentations that we have, are available on Channel 9 within 24 hours, so you can check it out. Thank you very much for your time. And I'll be in the big room if you have any questions, but I'll also hang out a little longer if you have questions you would like to ask me right now. So does anyone have any questions before my time runs out? OK, a couple here. You go ahead.
Yeah, you talked about, I guess, like how you use DirectX to replace GDI.
Sure.
But generally, I think it's like a focus on business apps and like Windows apps. I was wondering about managed
Sure.
DirectX and stuff like that.
So
managed DirectX, I guess, kind of died in whatever, like 2003, right? MDX. And then
strong word.
Okay, well, then XNA, which was more focused for gamers. So
Yep.
I was wondering, is there a managed? I know that there's the Code project or whatever.
Windows API Code Pack.
Yeah.
Yep.
Which I've downloaded and used, but I was wondering what the future is for managed DirectX.
Sure. So the question is, what's the future for managed DirectX? We had this solution called MDX 9 that was available. Actually, we called it MDX 1.0, but it was essentially for DirectX 9, available for a while. We have the concept of XNA Game Studio for people writing games, and we have the Windows API Code Pack for existing technologies. There's actually a talk just touching upon the Windows API Code Pack. What's the future of DirectX and managed? And pretty much what I can tell you is that we really are trying to make it something that is scenario-based, is the idea that when we have something like a line of business application, that's why we're trying to do something like the API Code Pack. And that's really the way that we're trying to go with providing those APIs and managed. And then in gaming, we have this really great platform that does a lot more for you when it comes to setup and models and all of that stuff through XNA Game Studio. And that's pretty much sort of where where we're looking at from the future. There's really not a lot more information other than that. It's that we provide these low-level advanced APIs for people trying to do high-performance applications using the DirectX platform for rendering. And we have the idea of, that people are still going to be using 3D graphics for gaming. We want to make sure that we nail both of those scenarios. And that's essentially what we provide in Microsoft. So.
I was wondering just to make sure that I guess, managed side will kind of keep up with it and won't just
Right.
fall into waste.
Yeah. Yeah, he said I want to make sure that things keep up on the managed side over the native side, and yes, we're aware of that. So, yeah. There was a question back here. You?
Can you talk about the NVIDIA GPU library and whether that's
So
NVIDIA has got its own
Right, it's CUDA. You're referring to CUDA. So the question is, can I elaborate a little bit on CUDA and what CUDA has to offer? I'm going to say no. If you want to learn more about it, you can come to Chaz Boyd's talk on Thursday on direct compute and ask him, because we're going to be talking about the direct compute solution, which is our generalized purpose parallel processing system, and he can talk about the differences between that platform and CUDA there. I can actually talk to you a little bit more offline if you'd like to learn a little bit more about the differences. Uh-huh. The question is, will the canvas in HTML5 and IE use Direct2D? I don't have data for you on that right now. Yes? Great. So there's a question that comes up a lot. What's the trade-off, or like what's the difference between WPF, or what does WPF use in doing its graphics over Direct2D and DirectWrite? And I really want to drive home this idea of different scenarios. The low-level advanced graphics that you might want to use Direct2D and DirectWrite for is when you're trying to write things directly. When you're trying to write an application that is really, you don't want to have that fine level grain of control, we encourage that you use WPF to get a really full, rich application. And the important thing to note about that platform is it currently uses DirectX 9 to do its rendering. So that's currently based on the Direct3D 9 platform. Question up here.
Kind of on the same vein, WPF added the D3D image stuff.
Right. So the question is there any plans to tie in Direct2D and DirectWrite with the larger WPF platform? I encourage you to come onto the floor and talk to the WPF guys directly, because they'll be able to answer that question much better than me. A way to think of this is that we're providing the lower level platform, that everything that can run on. And so the WPF team is really trying to address a bunch of scenarios, and it's interesting. It's something that they may be choosing to do in the future, but we're just trying to provide the good technologies that they may be able to build their platform atop. So the question was, can I mix and match textures sizes when I'm using an atlas? And the answer is yes. We actually have seen scenarios where you do that. Normally, we recommend you do that in powers of 2. So you have 32-bit, 32 pixel wide, and then 32 pixel wide, and then 4 of those make a 64, and so on and so forth. And if you do that kind of allocation, there are some more sophisticated algorithms you can use to make sure you're not sort of pounding over it. But the math is significantly more complex. So we recommend that you take textures individually and make them same size, and do larger allocations on another texture, so that you can keep the math a little bit cleaner. You can have the same algorithm used in similar size things. Although if you want to make it a single texture size to really pack everything in, there are algorithms to do that. You can find those online. I'm unfortunately out of time. If you have any more questions, feel free to come talk to me offline. And again, I'll be in the big room. So thanks a lot.